So just a little bit of background. Hopefully, most of you are familiar with rust fungi, but they're plant pathogens. They're named because they look like rust, so hence the name rust fungi. There are more than 7,000 different rust species, and it's probable that most plant species are actually infected by a type of rust. Now, the key species I'm interested in is obviously Myrtle Rust. That's what this webinar is about. But for the majority of my thesis, we weren't able to work with it in Canterbury. So instead, I was working with two model species. The common names are wheatleaf rust and poplar rust. These were chosen for a range of reasons, including relatedness, host type, impact / importance, and obviously crucially availability. No point having model species if you also can't work with them. Now, one of the biggest problems with rust fungi is that we can't grow them without their host plants. It's a huge limiting factor in how we study them and what we can find out, and it's going to be a huge feat to get them to be able to fully reproduce without their plants. So I'm sort of trying to get that started by seeing how they respond and grow on various flat and heterogeneous artificial surfaces. So I thought I'd go through their asexual reproductive cycle just before moving on, so that the terms that I use later on you'll be a little bit more familiar with. So to begin with, you have a dispersed Uridina spore. I'll just call these spores from here on in because it's slightly easier. That spore will land on and adhere to a plant surface. It then forms a cylindrical growth platform known as a germ tube. This will grow along the surface of the host and search primarily for stomata, but in the case of Myrtle Rust, it has less preference and produces more force, so it doesn't seem to mind. But for most rusts, once it's found that stomata, it then forms a balloon-like structure known as an aprosorium. From this, a specialized drill bit, known as an infection peg, then penetrates into the host. That then forms both historia for obtaining nutrients and intercellular hyphae for establishing a dynamic network within the plant. Once that network is established, it then forms a pustule below the surface, which fills with spores, erupts, and now you have, once again, spores that can be dispersed. So I thought I'd sort of start with my work by just showing you essentially some nice pictures. So these are some rust fungi germinating on flat artificial surfaces. So the one on the left is wheatleaf rust on flat agar-based media, and the one on the right is Myrtle Rust on flat PDMS. Thank you to the colleagues from Queensland for doing that work for me. So I work with both the agar-based media and silicone-based. PDMS is essentially just a silicone-based polymer. But from these images, you can see the spores for the wheatleaf rust, but you can see the germ tubes for both of them. Then we have that swelling that I was talking about, that aprosorium formation, and then those infection pegs that are trying to then grow into that media. So I grew rust fungi on a range of agar-based media with different agar concentrations ranging from 0.5% all the way to 6%. On wheatleaf rust, they were able to grow on these surfaces really well for the first 6 hours, with an increase in total germ tube growth being quite rapid. Between 6 to 12 hours, that sort of slowed down, and really from 12 hours onwards, we didn't see a huge increase in that total germ tube growth. You can see this on those bottom images there. So those are some wheatleaf rust spores. And even, for 2 hours, we've got quite long germ tubes, and then they are progressing. But really from 12 hours onwards, these particular spores had no real growth. I'll just point out that that orange sort of color that I've put on there is just to make the invasive growth a little bit easier. So that's the growth that went below the surface. With poplar rust, you can see first and foremost that it produced longer average germ tubes than wheatleaf rust, and it did so with a really good growth from 0 to 12 hours, and then still a pretty good growth increase from 12 to 24, but a much smaller growth increase between 24 and 48 hours past inoculation. And once again, just like with wheatleaf rust, there was nothing more after 48 hours. We did see for both of these that it had a preference for lower agar concentrations over the higher ones. It's possible that this is because they are less stiff, but also a little bit more wettable. So I mentioned that invasive growth. So we termed anything that was growing below the surface as invasive growth. And I've tried to show that with those pictures on the left, which are on different z-axes. So you can see the red ones starting on the surface, and orange to then yellow is just moving progressively further down. For the wheatleaf rust at the top, for those particular spores, they were growing to around about a 300 micron depth. For those particular poplar rust ones, they were going to around 95 micron depth. But this doesn't necessarily reflect the overall average invasive growth length, because you can see with that table next to it that the poplar rust did in general have longer invasive growth, which isn't surprising considering it was longer in general on the surfaces. We did see a tendency for more invasive growth on those lower agar concentrations. Again, it's possibly because they are less stiff, so it's actually easier to grow into them. With the wheatleaf rust, you can see that it did have a clear preference for that 1% agar, which was also the best one for just general growth as well. Now, I've grown these on a few different surfaces, but I thought I'd sort of pivot and talk about those heterogeneous surfaces that I mentioned. So those are leaf surface replicas. So I used a protocol that was previously designed by Rebecca Soph and optimized it for a particular plant species that the rusts infect. So this process in general begins with fixing a leaf to a surface, so in my case, a petri dish. You then have to dry it before casting it in PDMS. Now that drying phase is something that's quite specific to the plant that you're using. So if you don't dry them enough and you try to bake it later, you'll get bubbles, or you might have liquid that then prevents curing of the PDMS. If you over dry them, it can start to degrade, and then you get sunken features, and it just doesn't represent the leaf in its living state. So that's something that you've got to be careful with, as well as the baking. If you bake things at too low of a temperature, it can take too long, and you start to get that degradation, and you can get staggering of the features. If you bake too high, you'll likely just burn the leaves, and again, that'll just cause a staggered imprint, which isn't ideal. But once you've baked it, you then peel it off, and you have the imprint or the negative of that leaf. Sometimes you need to digest the leaf material, but most of the plants that I worked with were fine. You then chemically treat it to make it hydrophilic, coat it again with PDMS, bake it, and then hopefully get something like these images here. So we've got the PDMS wheatleaf replica on the left and the PDMS poplar leaf replica on the right. So I was able to get really, really good detail from this process after optimizing it. Can get the veins and the stomata really, really well, but can also get the trichomes. So I don't have them in focus with the poplar because they're mainly on that central vein, but with the wheat leaves, they cover, majority of the plant. There's heaps of them. I've tried to focus on them in half that top left sort of image, but if you just look at that big one, all of those black holes are actually trichomes, and if you focus the microscope considerably higher, you can see them at the top. And so we were really, really happy with these, but then we also wanted to make them out of that agar-based media. So the biggest difference between these is the treatment, the obviously casting material, and then instead of actually baking, we just cure them. But the treatment phase was one that required a bit of optimization. So the chemical treatment didn't work. We wouldn't get any of the features. It was too thick and incompatible with the agar. Tried no treatment, but unfortunately PDMS is very hydrophilic, and agar-based media is hydrophobic, and agar-based media is hydrophilic, so they weren't compatible. You get lots of bubbles. If we tried no treatment but degassing, same thing. But actually, if I treated it with oxygen plasma to make it temporarily hydrophilic, we were able to get results like these ones here. So these are the wheat leaf again on the left and poplar on the right. Again, we're able to get a lot of those features really, really well, able to get the whole leaf from poplar still. We're seeing those veins and those stomatas with similar level of detail to that of PDMS. We did, however, lose the majority of the veins from this process, And in part it's because it's too thick to actually get into those tiny little trichome needle-like holes that are in the imprint, but also when peeling it off, it's very easy for them to just break off. We weren't massively concerned with this though, because those are often there just to protect the plant against pests and pathogens. We didn't think that it would be crucial for our experiments that we were wanting to do. Oh, I apologize. So what I was wanting to do was to obviously grow the spores on those and see how they respond to those surface features. So these here are wheat leaf rust spores. So we've got the agar-based media leaf replica on the left and the PDMS one on the right. So they were able to grow really well on these. These pictures are just from 6 hours after inoculation, so a really good growth within quite a short amount of time. We did see faster, longer growth on those agar-based media, but we also saw a lot of randomized growth, so without any sort of real direction. Whereas on the PDMS, we saw quite a lot of growing up the vertical channels and then making quite an abrupt sort of roughly 90-degree angle change in growth, and then growing sort of towards the stomata. This is something that's seen on the plants, and it's because the stomata are always following a similar pattern, and so it's something the rusts have adapted to in order to locate them. Because if the germ tube just kept growing up the whole time, it would never come in contact with any stomata. So we did see a little bit of that growth on the agar-based media, but not as much as we did on the PDMS. So this was really cool though, because it showed that they were likely actually recognizing those surface features, particularly on the PDMS, and then responding to them. Didn't see a lot of swelling over the stomata, but the frequency of them actually contacting the stomata was relatively low as well. This didn't aid in their overall growth and production through the asexual cycle though, so growth still stopped after 48 hours. This is the Myrtle Rust spores on their leaf replicas. Again, they were able to grow really, really well. I'll just put an orange box around that one to make it a little bit easier to see. But they grew really similar on both materials. They did sort of seem to grow a little bit longer on the PDMS one, interestingly enough. It's possible that they were having to search for nutrients or possibly searching for stomata a bit further. We saw some swelling over the stomata, but not a huge amount, and no sort of defined growth like we did with the wheat leaf, but that's not unexpected because the features are a lot more randomized on poplar leaves, so they don't have the same typical growth patterns that wheat leaf rust has. Now, I wasn't able to get the same growth data with the lengths as I was on the flat media, and that's because the features are too different in height that it wouldn't be an accurate comparison. But we were able to look at the number of germ tubes and branches on these surfaces to see if there was any difference. So with wheat leaf rust, on average with the agar-based media, sort of had around 3, slightly lower on 1%, but that was again their most favorable agar concentration. But we did see less germ tubes on those leaf replicas, particularly on that PDMS one. And this is possibly another indication that they were in fact recognizing those surface features and therefore not putting out as many germ tubes to search for them. So that was another really good sign. Myrtle rust, it was a lot more variable, a lot more randomized, not a huge indication with the agar-based media leaf replica, but there was lower numbers on the PDMS leaf replica, so that could be related to what I was seeing, where they were sort of putting more energy into one really long germ tube, possibly trying to search for either nutrients or the stomata. So where did we really get up to? So we were getting up to that sort of 5th stage on that asexual reproductive cycle. They had a preference for lower agar concentrations, showed some surface recognition, particularly from wheat leaf rust and particularly on that PDMS leaf replica surfaces. We had growth up to 48 hours, but nothing further than 48 hours. But that's not surprising. I think it's going to need to focus more on specific chemical components and possibly even a multi-layered artificial media. These are a complex organism. They're not going to go through their entire asexual reproductive on a simple media, but it has been a really good indication to see them being able to grow and have differences between the media that we've been testing. So I'll just quickly talk about the other part of my thesis. So that's working with a lab-on-a-chip device that was previously designed by Yilling Sun. So this is a microfluidic device. It's a 3-layer device, and it allows for single spore capture using a flexible membrane. It also provides a channel for germination and uses micropillars for force measurement. So these pillars allow you to quantify the effects of control agents. You can also place them at different lengths so that you could see, say after 2 hours of germination, how does a control agent impact growth versus after 12 hours of growth. These are also really beneficial because they don't require plants. So for Myrtle Rust work in particular, a lot of those plant species that it infects are Tonga species. So we don't want to be just using them straight off the bat. A device like this allows us to test and ensure that agents are in fact having an impact, and then we can go to plant studies. But it's also beneficial because you don't have to take into account a plant's immunity. So it's an isolated system. So hopefully we can get it fully working, but they were originally designed for waterborne fungi and oomycetes. So rust fungi are obviously very different. And so there's 3 key things that I've been optimizing. First is just the dimensions of the device. So rust fungi are larger but produce smaller germ tubes. So the channel dimensions and capture space needs to be different. Spore preparation was actually a big one. So with the waterborne fungi, you don't really have to worry about that as much, whereas when we're taking something from plants, you can get a small amount of plant debris, and that can block up channels. So that's what's happened in those bottom images there. So that's not actually where we want the spores to go. It's simply a channel that we use to get them to where we need them to be. But because of debris, a channel got blocked up, spores got trapped, and then they sort of stayed there. But it was also a good indication that the internal conditions were suitable. So we need to dry these channels out, but still maintain a really high humidity. So I've been trying to do that. But obviously it was suitable enough for them to grow in that environment. So we're just working on getting them to the right place and making sure that the filtering process isn't reducing the viability of the spores. So that brings me to the end of my talk. Just want to thank everyone on this page for being incredible and super helpful, and also just thank Marge and Jenny for inviting me to talk on here. Thanks.
Thanks, Sarah. That was really, really cool. Audience, if you have any questions, please put them into the chat box, and I will ask them for you. And I'm going to start off with a question, because so you'd mentioned with the lab and the chip experiment that you have that the spores need to germinate and the germ tubes need to grow. How long would the germ tube need to be in order to be able to reach the agents?
So that depends on where we put the pillars. So I haven't actually put pillars in the device yet because it makes it more complex to fabricate. So just trying to see actually how long will they grow after certain times as to where we'd put the pillar. So ideally it would be, anything from, 100 micron all the way, to 800 micron. It would be good to be able to put pillars in a range of spaces, but they're going to need to, produce really at least a 100 micron germ tube. But they do that quite easily anyway, so it shouldn't be an issue as long as they grow in the right direction and in the right place.
Like, go this way. No, the other way. So a question is coming. What is the chemical composition of your agar media? Is it only water agar, or do you have nutrients in it?
No, so we have nutrients in it. I won't say the specific nutrients, but hopefully we'll be publishing this soon, so you can see that when we do publish it. But yeah, it's not just straight agar, but it is a relatively simple media that's commonly used.
Awesome. Sounds good. So the other thing that you had mentioned was having the multi-layer surface to grow these spores. What other sorts of things would you like layer the agar over the PDMS, or do you think, are you thinking of like other sorts of layers to put on them?
Probably not the PDMS, because it doesn't actually have any real nutrients and it's quite stiff, so they can't grow through it, but possibly just different layers of agar-based media, so even different concentrations. There's some research that looks into cellophane, which is a relatively flexible material, and if we had a cover of that and then try and get them to go through it into a media that has the nutrients that they then need for that part of their growth, looking at that sort of thing. So kind of trying to mimic more of the plant structure, and then the nutrients associated with those different levels.
Sounds great. So you mentioned that you've had and I know about the difficulty about getting access to Osteoproxenia cediae. And so do you now have permission to work with it? And is that's the next challenge?
Yeah. So we now have access to work with it. So hopefully over the next month or two, I'll be doing a lot of those experiments that I've done for the other rusts with Myrtle Rust, and seeing how they respond to those surfaces, see how long they can grow for just on those surfaces. But also I'll try and get them to go in the lab on a chip and see if they're happy in there, because they grow on the PDMS easier than the other rusts actually, which is just another demonstration of how hardy they are in comparison to the others.
They are, and then also like just the way that they grow, of like just punching straight through the epidermis. Do you think that that's going to be like make things easier for you, or a little bit harder?
I mean, hopefully easier. There are different types of dyes that you can use that can also measure the impact that they're using to drive into something. So that's a material we can mix in with PDMS that we were interested in testing, but obviously with time restraints we're not going to get to. But it'll be interesting to see how quickly they grow into the media. And also, it might be if they grow really well in the 6% agar, it might be that we look at seeing how concentrated can we make that media and still have them push into it, because they try to invade the PDMS, which is so much stiffer than agar that it was actually really impressive to see that. Could be slightly problematic in chip, but that's something we'll have to see when we can put them in there and test it.
Sounds good. And are you going to use like a different leaves as replicas, or are you thinking of just one or two?
So long term, it would be good to use a range of different leaves and see how they grow, because obviously they all have different features. But for my thesis, I don't know that I'll even do any of the leaf replica work. It might be something later on that I may get a chance to do.
There's
but it's
always a postdoc.
Lab on a chip. Yeah, exactly.
Well, thank you again so much, Sarah. That was really, really fascinating. So a video of today's webinar is going to be made available on the Beyond Myrtle Rust website in the next couple of days. And it's also going to be emailed to everyone who's registered. So our next webinar is going to be on October 25th. At 11 again. We'll hear from Grant Smith, who is at Plant and Food Research, about fungal transcripts and effectors. So keep a lookout for the webinar invite next month. So thanks to everyone. Hi, Raira. See you next time.